2, a little bit we got left, and then we're going to roll into chapter 4. So last time we talked about really conversions, dimensional analysis. So as we talked about, remember that the idea behind sort of dimensional analysis is to set up your problem so you could clearly see what units are canceling, which ones are not. And from any sort of inequality, which is something like this, we could write 2 conversion factors, which once again we could use or not use. In a particular problem, we most likely will use just one of them and not both. And we use whichever one really is opposites as we do these sort of problems. So opposite in terms of the units. So here, the unit A and unit A would cancel, and we would end up with our unit B in this case. Once again, we would be multiplying on the top and coming back and dividing by whatever's on the bottom. Remember that when we do conversions, you basically set it up like that, and you should set it up like that. In terms of significant figures, a lot of times it's sort of the original number that we use, but there are, again, some conversion factors that you do have to look at the significant figures. And those are typically the ones that cross over from metric to English. Again, if you're using anything that is sort of an English to English conversion or a metric to metric, you don't have to worry about the sort of significant figures there are in those numbers. But again, if you do cross over, you should look at the significant figures that are in those conversion factors. So what we have left in this chapter is density, to officially talk about density. So density is basically the mass of an object to its volume. And typically density has units of grams per milliliter, or grams per cubic centimeter is a very common sort of unit of density. They have both of those units. The grams is the mass part, and the volume is the volume part. Obviously, they're in milliliters or cubic centimeters. A reminder that 1 milliliter is the same as 1 cubic centimeter. So very commonly, if we have a liquid, we can put it into something like a graduated cylinder and take an actual volume reading in milliliters. If we have a solid, we could take 3 sort of length measurements, each like in centimeters. So centimeters times centimeters times centimeters will give you the volume of that object. And again, that's how we get something like this guy, by taking the length times the width times the height. Once again, all in centimeters, for example, which gives us our cubic centimeters. Now, the density of an object determines whether or not, for example, something will sink or float. For example, water. Water has a density of pretty much 1 gram per milliliter. So if you ever need like the density of water, that is typically the number that you use. I will tell you that density does change with temperature. So as the temperature changes, so does the density value. But in most cases, book problems, normal problems, you just come across a situation where you kind of need the density of water. Most everybody will just assume 1 gram per milliliter, but it actually does change with the temperature. So anything that is more dense than water, which is right about here, will sink, and anything less dense than water will actually float. And if we put a bunch of solutions into like a graduated cylinder, and they are different densities, they will separate out into sort of different layers because of that, where the bottom layer here, if that's our bottom layer, I guess really that would be our bottom layer, would be the most dense. And up here, whichever one's our top layer, would be the least dense in this case. So if I threw something in there that's like a solid and it gets trapped right about there, that means that it is actually more dense than anything that came above it, right? And less dense than anything that came below it, as it would float in there. Now, when we calculate density, these are, again, the typical units for things that are liquids or solids. Those are typically what we see. We don't deal with it too much in here, but a lot of times gases will actually have units of grams per liter for their density. But most of the time in this class, we really won't see that. We will see the grams per milliliter or grams per cubic centimeter. The number there goes with the mass part of the grams, and it's always 1 milliliter or 1 cubic centimeter. So Density is mass divided by volume. That means that volume is mass divided by density. That also means that mass is volume times density. Sometimes people remember this by like the DMV triangle. Everybody loves the DMV. DMV, there we go. So density is mass over volume. Volume is mass over density, and mass is volume times density. So that's a quick way you could remember how to rearrange that particular equation. You do need to be able to rearrange this formula and really solve for any of those three things. We very commonly will solve for density, mass, or volume in problems. So you may be given two of the three and has to solve for the other thing. So you definitely need to make sure you know how to properly rearrange that to solve for what you're looking for. Any questions on that there? Now, substances that have a higher density usually contain particles that are packed in a lot tighter to one another. The one very common exception to that is our friend water. Yes, when we have the solid version of water, what is the solid version of water? That is ice, they call that, right? When we put ice cubes in our cup, it ends up on top, right? It starts floating in liquid water. So water is a very unusual substance in most things. In their solid state, they're much more dense than their liquid state, but water actually is a lot more dense in its liquid state than actually in its solid state, which is why things like ice will float. And that's because when water comes together, different water molecules, when they are together and they start to freeze, they are attracted to one another. And what ends up happening is in between water molecules, because of the way they are sort of bound together, which is known as hydrogen bonding, it creates a lot of open areas between the water molecules. So they cannot like get super tight to one another. And if we think about the density formula, which is density is mass divided by volume, what that's going to create is all this open space between the different water molecules, which means it's kind of bloated. And the volume of ice is actually going to be much larger than it is in liquid water. And because when I have a larger number on the bottom here, that means my density will actually be a smaller number, right? When you divide a small number by a big number, you get a small number. So because of all that kind of open area that happens between different water molecules, they really, as odd as it sounds, can't get as close as they can in the liquid phase because they have a little bit more energy. So they're able to kind of get in there a little bit closer to each other, creates this kind of swelling of the water molecules, creates a larger volume, and the result of that is a smaller density than what we see. And again, that's a very unusual sort of characteristic. Most substances are really the other way around. In their solid state, much more dense and packed in there much tighter than in their liquid state. As I mentioned before, we probably won't see too much in terms of the units for gases, but mainly these are going to be the units that we could get it. And again, the volume part is really found by just taking a reading, reading the meniscus. And again, if you have some type of solid, taking those length measurements and multiply them together will give us another way that we can get to a volume, which is cubic centimeters. So here's some density of common things. And I would say out of all this list, you really should know water. And again, that's the one that's going to kind of pop up the most. Anything else you could kind of look at it. But pretty much, as you can see there, just comparison. Here is ice, which once again is the solid version there of water. And you can see it has a density of 0.9 versus 1. That's actually the maximum density there at 4 degrees Celsius is really the largest density value that you'll find for water, which is at 1 gram per milliliter. And again, you can see some solid guys here we would expect to sink, and then obviously some other guys there would obviously float in water. If I take like a Diet Coke can and a regular Coke soda can and I put them into water, will they both sink? Will they both float? What will happen? Well, actually one will float and one will sink. It's a good party trick. Yes. I would agree with you 100%. So it's a good party trick. Like I said, you could try that out. But actually, you take a can of Diet Coke, take a can of regular Coke, and when you put them in there, actually the Diet Coke will float. And that's because, as you correctly said there, the regular Coke has a bunch of sugar, right? Because it makes it more dense. Diet Coke's got artificial sweetener, so not as sort of dense. So actually, the Diet Coke guy will actually float while the Coke guy will actually sink. So that's fun. It's fun party games, you know. You take a glass, you take some like 7-Up, and you throw some raisins in there, and they'll start dancing. Other party games, that's all right. When you're watching football later in the week, you can do that. All right, so let's talk about a very common way that we get density, or the volume, when we're dealing with density, which is volume by displacement. So really a very common way, especially when we're dealing with density to get the volume. As I mentioned on the previous slide, there's really two ways. We talked about getting a volume. You could just simply take a volume reading. If it's a solid, you could use a ruler and measure it. But very commonly, we could do volume by displacement, which means that if you take a volume of a solution like water and you put it in something like a graduated cylinder, and if you take some type of solid and you basically put it into that cylinder that has the water, what will happen is the water level there will rise in the cylinder because of the solid that went in, and we'll have a final volume. So what will happen in this case is when you put a solid into something like water, it will actually displace a volume that's equal to its own volume. So to find the volume of the object that you put in there, it's really the difference between those two volumes. So you can find the volume of the object by taking the final volume minus the initial volume, and that is a very common way that, you know, we can find the volume of a solid object super easy. Just put some water in, drop it in, and take a reading and stuff like that. So that's what we see here. For example, in this this problem there, they got some zinc. They have the mass of zinc right about there, and they had a initial volume, which looks like it was 35.5. They have a final volume after they put the zinc in there, which was 45.0. Now, when they do the math here, we do want to kind of watch our significant figures. We do need to do the subtraction part first. And when we do the subtraction part, we are looking at decimal places. So when we do the subtraction, I'm going to go with their number and hope it's right. It's 9.5, which goes to one decimal place, which is what it should. The last thing that we would do would be to take the mass and divide it by the volume. And when we're dividing, we look at significant figures. So we do have to switch gears. This has 4 significant figures like it shows. That has 2 significant figures like it shows, which means our answer should end up with 2 significant figures. So sometimes when you do these calculations, you may be doing the subtraction part first. So you want to think about, again, decimal places, but now we're doing division here at the end, maybe multiplication. So you need to think about the number of significant figures. And this is 7.2 grams per milliliter. When you do have a density given to you, you could think of it like a conversion factor. And what that would mean is, in this particular case, there's 7.2 grams per 1 milliliter. And we could use it in that sort of form if we want to do a little dimensional analysis sort of calculation. We could also flip it around if we needed to divide by it and get 1 milliliter is 7.2 grams. So we can use density if it's given to us more like a conversion factor and sort of set the problem up like we were dealing with our dimensional analysis, so you can see the units canceling. So don't be afraid to sort of flip it around. But what we do see is, as I mentioned before, the number stays with the grams part, and it's always 1 milliliter or 1 cubic centimeter for the volume part. Any questions on that there? All right, so what is the density of 48 gram sample of metal where the cylinder rises from 25 to 33? So why don't you take a second there and calculate what. Okay, let's take a look. So obviously we're dealing with density, which is our mass divided by volume. In this case, we are given the mass, which is 48.0 grams. We have our initial volume, of 25 milliliters. We have our final volume of 33 milliliters. So really, we do have the density and the mass given to us. So we got everything we need to get to the density. We have the mass and the volume given us. So we have everything to get to density. We do have to do our volume by displacement. So we started here, we ended there. So again, the difference between those two is going to give us our volume. So the volume of our object here will be our final volume minus our initial. So our final volume being 33.0 milliliters minus our 25 milliliters. And that's going to give us, it's going to give us 8.0 milliliters. The reason I put the 0 is it should go to 1 decimal place. So again, if I got rid of the 0, I'm going to be in trouble in my next part of the calculation, right? Because I will have the wrong sig figs. So now that we have that, our density here is going to be 48.0 grams divided by 8.0 milliliters. And in this case, we'll take 48 divided by 8. 6.0 grams per milliliter. Once again, the number stays with the grams part and is per 1 milliliter. The one here again that determines really how many sig figs we should end up with is the volume calculation, right? So based on that is sort of where we end up in terms of our answer. Any questions on that one there? That's good. They agree. That's even better. All right. So obviously, if we know the density and the volume, we could get to the mass. So why don't we try one here? An unknown liquid has a density of 1.32 grams per milliliter. What is the volume in milliliters of 14.7 gram sample of a liquid? Okay, let's take a look. So once again, obviously we're using density. And if you're not sure, we got the density given to us as 1.32 grams per milliliter. We also have the mass given to us, which is 14.7 grams. So if you're not sure, I got mass, I got density. Volume seems like a really good one to solve for, since that is what it's looking for. Once again here, volume will equal mass divided by density, timesing volume to both sides, and then dividing by density back the other way. And that is how we get there. In this particular case, we can also approach the calculation like dimensional analysis. Like I said before, we could use this as like a conversion factor as milliliters over 1.32 grams. Then you really don't have to worry too much about rearranging the equation. You get to just end up with the units you need, right? So if you had something like 14.7 grams, I know grams there is on top, which means I would need to use this like a conversion factor like so. That will give me milliliters and 1.32 grams, which is essentially dividing by it like we were supposed to be doing. That gives us 14.7 divided by 1.32. Looks like 11.1 milliliters in this particular case. We have 3 sig figs there, right? And 3 sig figs there. So our answer should have 3 sig figs. Yeah. You can, as long as you show the units. I would just say sometimes it's better to show it this way. Again, in case you rearrange the equation wrong, you could kind of see the units aren't canceled out correctly. So sometimes it could help you if rearranging equations is maybe not your strong suit, or you're not sure if you rearranged it correctly. By doing it this way and kind of doing more of a conversion factor way, you can see, okay, well, if you, for example, accidentally wanted to multiply it, understanding dimensional analysis, you should see that these two are not going to cancel out. So that would be the wrong math to do. So sometimes, it's a good way to maybe check yourself if you need to. Yeah. Other questions? But as you could show it this way, you could show it by plugging it into the equation, as long as when you plug it in the equation, also has the units when you do it. Okay. Other questions? All right. So there's that. All right, let's try this one. John took 2 teaspoons of cough syrup. Syrup has a density of 1.2 grams per milliliter. And if there are 5 milliliters in it, Okay, let's take a look. So once again, obviously dealing with density. So we'll start with our equation. We have a volume that is 2 teaspoons. We have a density again given to us as 1.2 grams per milliliter. And we have a conversion factor that's given to us here in the problem. 5 milliliters is 1 teaspoon. So once again, if you're not sure, I got density going on, I got volume going on. So if I check the right one, that would be better. I'm still learning that alphabet. Let's see here. Let's try that again. All right, come here. There you go. All right, so I have density, I have the volume given to us. So mass would be a good thing to solve for. Once again, we're going to divide the volume to the other side, come back and divide by the density, and rearranging that will give us mass. Actually, in this case, is volume times density. In this case, since we are looking for the mass and not the volume. So in this case, we once again can use this as a conversion factor if you want to take a more dimensional analysis approach. Again, if you're not sure how to rearrange it, you just think about what units you need to end up with. And in this case, we need to end up with grams. So that is the approach. We obviously cannot use our volume in teaspoons because it does not match the volume that we see in the density. So we do have to do a conversion before we could use it. And that is where this will come into play. So we'll do our 2 teaspoons. And once again, going opposites to cancel. 1 teaspoon on the bottom gives us 5 milliliters up on top. Going to give us 10 milliliters in this case in terms of our volume. At this point, we can then use our conversion factor. So continuing on, we see milliliters up on top. So we actually need to use it in this form here, which will be multiplying. And once again, we can see that the units cancel, leaves us grams at the end, which is what we're looking for. So we'll do a 10 times a 1.2, going to give me a 12 on that grams in this particular case. First off, any question on the calculation? You can use the formula if you like, yeah, and plug it in. It's the same thing. But again, as I was just mentioning, you might want to show it the other way so you don't screw up rearranging the formula, which is a very common mistake people make. Good question. So there can be multiple ways that you could get there. You need to show the work however you show the work. This is the way in chemistry they want you to show the work, which is dimensional analysis, showing the units and stuff like that. But again, if in some of these where we have formulas, if you want to plug and chug into there, as long as you show the units and all that, when you plug and chug it in and rearrange it correctly, it's okay too. Yeah. What you cannot do is just lay down numbers everywhere. Yes, with no units, no organization of how the calculation came about, and just rando numbers on the page. Yeah. So got to have some type of organization to it. This is a very organized way of doing it, and probably a best way of doing it, as I mentioned earlier. Sometimes people think they are rearranging the equation correctly, and they're not. And so if you could just follow sort of the unit aspect of it, all you have to do is make sure that you end up with the correct units at the end, and it will help you in some cases. I can't tell you how many people will, in this case, for example, at the end, divide instead of multiply, right? Or in the previous one, multiply instead of divide. So setting it up that way with dimensional analysis can help catch some of those errors that sometimes people will make when they go through the problem. But regardless, you do need to show work that has units, and again, an organized sort of fashion of how you did the calculation, not just numbers on the page. Any questions on that? Yep. All right, so in terms of significant figures, we got 2 sig figs there, 2 sig figs there, which is why we should end up with 2 sig figs there. Last thing we did is multiply 2 sig figs by 3 sig figs, which means we end up with 2 sig figs for our answer at the very end. Any questions on any of that there? Hopefully they agree. That's good. All right, any questions on density or anything like that? All right, well, we ain't doing this, so we're good with chapter 2 now. All right, so don't worry about specific gravity from chapter 2. You just have to go through density. All right, we're going to go off to chapter 4 now. Up here, so we're going to go to chapter 4, as we talked about, I think, last time. Again, chapter 3's lecture has been posted, so make sure that you do watch it. You are responsible for it. Again, with the no day on the first day, the holiday, and all that, just to try to keep us somewhat on pace here. So we're going to go to chapter 4 next, which is going to talk about atoms and elements. We'll talk about, obviously, the structure of the atom. We'll talk about protons, electrons, neutrons, and then we'll talk about electron configuration towards the end of the chapter there. So let's start with elements and their symbols. So elements, I guess there is a periodic table. Elements can be found on the periodic table, and elements are basically as far back as you could go with anything. You could break everything down to elements, but you can't go any further. So elements are oftentimes thought of as being like the alphabet. There's only so many letters in the alphabet, but you can make all kinds of different words depending on the combination that you put together. So kind of a similar idea here. We can make different types of compounds as we put different elements together. The basic unit of an element is an atom. And as we'll talk about in this chapter, they contain protons, electrons, and neutrons, where protons are positively charged, electrons are negatively charged, and neutrons have no charge. Now, when we write our symbols for our elements, they really are either kind of one of two ways. They may be a one-letter combination, no, one-letter symbol, which if they are a one-letter symbol, you do capitalize the symbol or the letter. And if it is a two-letter symbol, like what we see here with aluminum, we do capitalize the first letter, but we do not capitalize the second. So it would be one or letter symbol or a two-letter symbol. And again, we do not basically capitalize both. Elements are pure substances, which are really what everything else is built upon. They cannot be broken down any further, as I mentioned. But if you do have sort of the compounds, you can break that down further. So if you have water, it can be broken down into H2 and O2. This is a compound. These are elements. Hydrogen gas, oxygen gas. That is naturally how hydrogen and oxygen comes. And there are certain elements that actually come as what are referred to as diatomic molecules. And common elements are H2, O2, N2, Cl2, F2, Br2, I2. So these 7 here is how each of these come. Most of them are gases, not all of them, but most of them are gases. And that's how they naturally come by themselves when they're not combined with anybody else. So you never have hydrogen just like an H floating around. It's actually hydrogen gas. It's really 2 hydrogens together. Oxygen comes as 2 oxygens that are bound together. And nitrogen, for example, comes as 2 nitrogens basically bound together. So all of these guys, because they only contain atoms of the same element, these are all elements. They are also all molecules. They are not compounds. So they are not compounds. Water, on the other hand, is a compound. It is also a molecule. It is not an element. So water is both a compound and a molecule. So we might have talked about it earlier, and we might see it again here, but there is a difference between a molecule and a compound, which oftentimes confuses people. A molecule is basically just 2 or more atoms that have come together. And that may be 2 or more atoms of the same element or different elements. It doesn't matter. You basically just need 2 atoms of anything to come together to make a molecule. A compound, on the other hand, needs 2 or more atoms of different elements. So that's what we see here with water. Water is hydrogen and oxygen together. So that is two or more atoms of different elements that came together, which makes a compound. It also meets the basic definition of two or more atoms that came together, which is why it's also a molecule. It is not an element because it contains atoms of two different elements together. It contains hydrogen and oxygen together, so it's not an element. That is why hydrogen, H2, is an element because it only contains hydrogen. It's also a molecule because there's two or more atoms together. It is not a compound because it only contains hydrogen, no other elements involved. So again, that is the difference between a molecule and a compound. You could think of a molecule as really just a basic definition of all you basically need to meet is there two or more atoms together? And if it is, it's a molecule. In order for a compound, you need at least two different elements be involved for it to be a compound. Any questions on the differences there? Now, compounds can be broken back down into elements, so you can break compounds back down into elements by some type of chemical change, chemical reaction. Like my example here, we could take a compound like water and break it down into its elements. At that point, you can't go any further. So you can't break down the hydrogen or the oxygen any further. That is, again, as far back as you could go, which are those elements. Any questions on that? So here are some of the names. And once again, you can see capital letter and capital and lowercase. The reason we need to do it like that is if we take something like this, capital C, lowercase o, and capital C and capital O. If you're somebody that sort of capitalizes everything when you write, you should not do that when you're writing symbols. Capital C, lowercase o is the element cobalt. Yes. Capital C, capital O is the molecule or compound known as carbon monoxide, which is very different than cobalt. So you may be actually saying something you're not meaning to do if you capitalize both of them. So again, this is carbon monoxide, and that is cobalt. So element, compound, yes. So two different things. So it's really important to make sure that you capitalize the first letter, but not second. Now, element names and symbols, they come from a wide variety of sources. They come from origins of where they were discovered. They come from, Greek and other type of history type names. So we do have some different ones. When you look at the periodic table, I would say at some point here, when you look at the periodic table, definitely those guys to the left in the first couple of columns, you'll usually see like a staircase that kind of comes down. Usually all those guys to the top right of the staircase or to upper right, a little bit below the staircase, and maybe the first couple of rows in the middle there are definitely the ones that you usually will have to sort of know. Yes. What's that? Carbon monoxide is a compound because it contains both carbon and oxygen, and there's two atoms involved. It's also a molecule because it contains two atoms. Yeah, it is not an element because it has two different elements involved. Yeah. Water is H2O, but when you break apart water through a chemical reaction, run an electrical current through it, this is what's known as electrolysis of water. You could break down water, which is a compound, into its elements, which is hydrogen gas and oxygen gas, H2 and oxygen. They would be separated at that point, obviously back into its elements. Other questions? Okay. So those are sort of ones you should know. Definitely as we go into the next chapter after this, we're going to talk about naming and all that. So there's a lot of rules that go with naming. So you don't want to at that point kind of be going like, what is the symbol for this element? So you want to have some of that sort of knowledge as you go through it. You'll get used to most of the common ones. And like I said, kind of what I drew, kind of to the left here, upper right, a little bit there, and kind of in the couple of rows there. We really won't deal with too much on the bottom here, and kind of the two bottom rows in the middle there. We probably won't see too much outside to the right there by the staircase. So at some point you'll kind of know a lot of them. So C is carbon, S is sulfur, nitrogen are common ones, hydrogen, CO is cobalt, sodium is Na, right? That is sodium, that's a common one. Potassium is K, that's also another very common one that we come across a lot. Silver is Ag, yes. Gold is Au. Mercury is Hg. Se, my favorite element, which is selenium. It's a good one in that. And also some other ones that may be iron, right, is Fe. And oftentimes confused by people is copper, which is Cu. So that is copper. And you have in your book, obviously, the periodic table and a list of all these guys here and the different symbols. But as we go through this chapter and other chapters, and here's some of the rest of them, you know, probably a majority of the ones that you see on this slide, not necessarily every single one, but a good amount of these guys are very common ones that come across a lot. So it looks like it's table 4.2 in your book. So make sure you do look at it. And again, you could kind of see where some of these symbols come from. These are sort of their origin sort type names as to where we get some of those, you know, how do they get Na for sodium type of thing, or Fe for iron. All right, so again, here are some of the other ones, silver and gold and their symbols. So let's take a look at these. The correct symbol for each of these. Iodine is I, yeah, it's just capital. Iron is capital F, lowercase e. Magnesium, which is not to be confused with manganese, that is capital M, lowercase g. Zinc is Zn, and lithium is Li. So again, capital letter for one letter symbol, capital letter followed by lowercase for our two letter in each of those. Any questions on any of those there? So let's take a look at each of these. So P is phosphorus. Ar is a noble gas, which is argon. Mn, which again, as I just mentioned, should not be confused with magnesium. This is manganese. Be is beryllium, and K is potassium. So again, I would say definitely we come across these guys pretty regularly, these sort of symbols. Beryllium occasionally, but not too much. But these other ones we do sort of see a lot, definitely, as we go through the different chapters. Questions on symbols or how to names? So again, better to start learning some of these very common ones. Again, it will help you out when we get into the naming part. So you're not doing two things at once, trying to learn the sort of symbols and learning the rules that we follow when we name things. All right, so let's talk a little about the structure of the atom. We're going to talk a little bit about the atom and some of the experiments, not into great detail, that led to sort of the understanding of the atom. The atom basically is the smallest sort of representation of each of the elements, as I mentioned. Atoms contain, as I said, protons, neutrons, and electrons. And pretty much all elements will have this, three guys, except hydrogen. So hydrogen is a little unusual. Hydrogen actually only has a proton and a electron, no neutrons. So all other elements will have all three, protons, electrons, and neutrons, but hydrogen is unusual and it has only a proton and electron, which is why we find hydrogen kind of over there, and it has some other sort of properties as we will talk about. So when we look at the atom, a lot of sort of early ideas about the atom was this idea that atoms were these very small, sort of indestructible sort of particles, if you will. And one of the earliest sort of ideas about the atom was one that was done by Dalton. He developed basically what is referred to as Dalton's atomic theory. And because it is a theory, it was found later on not to be correct in all aspects of it, but some parts of it is correct. And let's talk about some of the different parts of Dalton's atomic theory. He said that all matter is made up of these tiny particles called atoms. All atoms of a given element are identical to each other, and those of different elements obviously are different. Atoms of two or more different elements combine to form compounds. A particular compound always has the same type of atoms and the same number of atoms. So, you know, if you have water, no matter where your water is, here, Europe, in a bottle coming out of the tap, we're just talking about the water part. It should still always be 2 hydrogens and 1 oxygen, no matter what the deal is. Which means by mass, you should basically have 8 grams of oxygen for every 1 gram of hydrogen that basically pops out as water. He also said a chemical reaction involves only the rearrangement and separation of the atoms. We don't create nor destroy any atoms. And that is true in terms of a chemical reaction. Really, the only thing that happens is all the starting material, they pretty much break all their bonds, and then they reassemble on the other side, which are known as products, making new compounds and new bonds. Because they only deal with bonds, which are electrons, and never ever changes elements. And that's why, as you might know, and we'll talk about, when you go to have an equation, you need a balancing equation, which means if you start with 4 carbons on the left-hand side of the arrow, you should end up with 4 carbons on the right-hand side of the arrow. They may be in different things, but you shouldn't lose a carbon along the way or anything like that. So in a chemical reaction, we never ever lose any elements. We don't create any new elements along the way. And that's different than what happens in a nuclear reaction. In a nuclear reaction, you actually do nothing but create different sort of elements along the way and stuff like that. But in what we deal with in here, since we don't do the nuclear chapter anymore, we deal with just chemical reactions, which basically have really the conservation of all the elements that you start with, you end with. They're just in different things. So there are some parts of this that were found to be sort of incorrect. One of the major things that were found to be incorrect are, again, that atoms are indestructible. Again, kind of nuclear chemistry means you could kind of change an atom and stuff like that. And the other one is this, that all atoms of a given element are identical to each other. The existence of isotopes basically disproved that. And isotopes are the same element, but they have different mass. So obviously, if they are the same element, but they have a different mass, that means that their atoms cannot be identical, basically. As we'll talk about, they basically have different numbers of neutrons, which is why they have different mass. So everything else is correct. You know, we make a compound from a combination of a couple of elements. We break bonds and make bonds. We think of a reaction as just really a rearrangement. So those two things were sort of later were disproven not to be so correct. Atoms being indestructible, and again, that all atoms of the same element are identical to each other. So those are two things that are sort of incorrect. Any questions about that? Okay. So by the end of the 1800s, it was known that the atom was actually really small, but it actually contained an internal structure of even smaller particles, which are sometimes referred to as subatomic particles. And those are what we've been talking about: our protons, our neutrons, and our electrons. So although the atom is really, really small, it actually has an internal sort of structure of even smaller particles, our protons, electrons, and neutrons. And once again, these guys being positive, no charge, and negatively charged. So there was a lot of different sort of experiments along the way that helped us have a better understanding of these different sort of particles. And there's sort of an early model of what the atom was thought to be, and a more modern sort of version of the atom. But one of the important sort of aspects in chemistry is this idea of electrostatic attraction, which is basically the idea of opposites attract. So much like in life, when we get two things that have the same sort of charge, two positive people, not so nice to be around each other. Maybe they annoy each other. So same thing with the two positive charges. When two positive charges get near each other, they really don't want to be near each other, so they repel one another. Same thing, two negative people, that also is not a great day. So they don't want to really be bound to each other. So things that have the same negative charge or two negative charges to come near each other do not want to be there. But when we do get opposite charges, a positive and a negative, they are actually attracted to one another. And that's the basis of a lot of attraction forces and how molecules interact with one another, is really that basic simple idea that basically opposites attract. So when we have a positive and negative, they are attracted to each other. The strength of that attraction actually does increase with the sort of number, if you will. So for example, something that is like +1 and -1 will be attracted to each other. But if you put something that is +3 and -3 together, it will be even strongly more attracted to each other because it's a much larger charge. So as a charge increases with things that have charges, positive and negative, so there's sort of the level of attraction between the two because of those charges. So this understanding of sort of opposites attract also is very helpful in experiments that were done to understand the atom. And that's because in a lot of experiments, they use things like electrical fields, which has like a positive and negative side, and also magnetic fields, North Pole, South Pole. So if they shot a particle, for example, and it kind of tilted up towards the positive side of our electrical field, we would have a pretty good idea that that particle was what type of charge? Probably negatively charged, right? Because it's going to be attracted to that positive. And if they shot something and it kind of bent towards the negative field there, we would know that that guy is probably more positively charged. And my bad drawing there, but imagine that went straight. And we drew something or shot something, and the particle, I did not fix it at all. So let me just keep making it worse and going straightish. Goes straight through there. No deflection. That would mean that it has no charge associated with it. So things like protons, electrons, and neutrons, they sort of knew has some charges associated with them. So they could take advantage of that through these experiments to, really try to understand what happens. There's really sort of three types of radioactive particles that were also sort of used in these experiments, which sort of correlate to each of these type of charges. They use what are referred to as alpha particles, and these are radioactively positively charged particles. They use beta particles, which is the symbol like that, and those are negatively charged particles. And they also use gamma rays, which basically has no charge. So these are all radioactive sort of particles, sort of equivalent to protons. It's really a helium, equivalent to like electrons, and this has no charge, kind of equivalent to sort of neutrons and stuff like that. So having the advances of these sort of particles, the understanding of opposites attract, really helped a lot to understand the atom and what came out of sort of their experiments that happened. One of the major sort of steps towards understanding electrons was done by Thomson. He did work with what is referred to as the CRT, or the cathode ray tube. The cathode ray tube is a tube that shoots negatively charged particles, and it has like an electrical positive side and a negative side. So those particles would be heading towards the positive side. And he was able to do some work with that CRT tube to understand the nature of an electron, like those negatively charged particles. You might be familiar with CRT tubes, depending on how old you are. Old TVs that had backs, I know these things don't really, I know they have backs, but you can't take them off. There's actually, like a CRT tube in those. Old computer monitors that also had like the big back that came out of those. Those are CRT tubes. Your mom and dad used to say, don't sit in front of the TV because it was like shooting things at you. This is true. That's true. These things don't have CRT tubes, too flat, not enough room to put them in. But those are cathode ray tubes, and they basically shoot these negatively charged particles. That's how the old, when your TV broke, you didn't just go to Costco and get another one. You called the TV repairman out. They opened up the back of your TV and actually fixed it, so they tuned your picture tube on your TV. A lost art, I suppose, nowadays. Nobody even knows what I'm talking about. You could Google it, it's okay. But Thomson, I know, I feel old now. That's all right. All right. But Thomson did a lot of work with that. And what he was able to actually figure out was really sort of the charge to mass of an electron. And followed up with Thomson was another guy that actually was known as Millikan. And he did what is referred to as the oil drop experiment. And what he was able to do in his oil drop experiment was he had sort of a chamber that also had an electrical field sort of happening in it. And he shot oil droplets in there. And what would happen is the oil droplets would want to fall based on gravity, and they would pick up a charge. And he was able to adjust the electrical field in his little tube chamber there in such a way that the actual oil droplet just kind of hung there. It didn't go up, didn't go down. And he was able to really figure out the charge of an electron. And between the two of Thomson and Millikan, the mass of an electron was really able to be determined. And the mass of an electron is something like 909 times 10 to the minus 28 grams, give or take a gram or two. And that is a large number, a small number. It's a really small number. It's like 28 places this way, right? And put a bunch of zeros in front of it, right? So it's a very small number. So between those two experiments, what came out, it was really a much better understanding of electrons, these negatively charged particles that are in an atom, and really the mass of an electron. And that led to really the first understanding or sort of description of what they felt the atom was. And that was also proposed by Thomson. And this is what is sometimes referred to as the plum pudding model. And that's like an English dessert of rice pudding and raisins. And he felt that the atom was basically a sphere of positive charge. So he had all this positive charge spread out all over the entire atom, and embedded inside here on the atom were these negatively charged electrons. And he felt that most of the mass of the atom was actually made up of the electrons. And this was sort of the accepted model of the atom, where positive charge spread out all over the place, these really heavy sort of electrons built into it or kind of sprinkled in there like the raisins in the dessert. And this was really sort of the accepted model of the atom until really the next major event occurred with the atom, which was Rutherford and his gold foil experiment. And what Rutherford did in his gold foil experiment was he took pieces of gold foil, like we see here, and basically he shot alpha particles at them. So he shot those alpha particles, which are those positively charged particles. So what he expected to happen was based on Thomson's model, where we have this positive charge spread out and these electrons. He thought that by shooting these alpha particles, it should kind of go through and there should be some deflection happening, because that is positive versus positive, right? And they don't really want to be near each other. But the alpha particles are moving really, really fast. So they should be able to bounce through. So if you think about the atom as my paper here, not so much circle anymore, but more of this. And then this was all the positive charge basically spread out over the atom. If I shot my pin at it here, and somebody held one side and I held the other side, and this pin was moving really, really fast, it should be able to punch through, right? But it's going to kind of deflect as it kind of goes through, as it's going to be really tight. And that's what they really sort of expected to happen when they did their experiment. They were really surprised that that's frankly not what happened when they did their experiment. When they shot these alpha particles at these pieces of gold foil, they basically saw that most of the alpha particles went right through with no problem. Just kind of sailed right through. So most of them, what they saw just went all the way through. But they did see that every now and then they would have an alpha particle get sort of scattered at these large angles, would sometimes even come back at the source. So that was very surprising to them, because in order to make an alpha particle, which is a heavy radioactive particle moving quite fast, to bounce off at really large angles, It had to hit something that was very, what type of charge? Where things don't like to be near each other, things that are positive and positive, right? Positive, negative like each other. But if we're shooting alpha particles, which are positively charged things, in order to make that thing ricochet at these really large angles, it had to hit something very, very positive to do that, right? So that was really surprising to him. So for example, if we go back to my example of this being the Plum Pudding model, and this is all the positive charge, right? If I didn't have the positive charge spread out over the entire atom, but I took my positive charge, like you could do, and fold it here, right? And I fold it, where they say 6, 7 times is how many times you could fold a piece of paper before you can't fold anymore. Right. So now instead of my positive charge being spread out all over the place, my positive charge is right about there, yes? So now when I throw my pin at it, right, it is not going to be able to go through, right? It's going to bounce off at those really large angles. So what came out of Rutherford's experiment was the idea that, you know, this Plum Pudding model, not so good. We have to sort of come up with a much better sort of model of the atom. And they did. So what he's basically said was that the atom is mostly empty space. And that's what accounted for all those alpha particles that sailed through with no problem, were not deflected. They just went straight through. They hit nothing, basically, right? Just like if I took my pen and I threw it at, and right there in the openness, it's going to fly no problem. It's not going to bounce off. It's not going to hit anything, right? There's nothing in its way for it to be deflected. He said that an atom must have a very dense positive core, which they called a nucleus. And it was later found that protons, which are positively charged, are in the nucleus. And later on in like 1930s, neutrons were found in the nucleus that has no charge. And out from the nucleus at some point is our electrons traveling out from the nucleus. And really the other major difference is the idea that most of the mass of the atom is actually the nucleus and not the electrons, which was a major difference between that and the Plum Pudding model. So we have the nucleus, which is really positively charged in the center, which has our protons and our neutrons. We have our electrons. And as we will talk about, by the way, electrons do not travel in pretty circles. They actually travel pretty randomly around the nucleus. They don't sit in orbits and go in nice pretty circles or anything like that. They are randomly moving about really the empty space. So all that empty space is where you find electrons basically moving about in a random motion. Should there be any attraction between the electrons that are flying around and the nucleus, which is technically positively charged? There is, right? Electrons are negatively charged and the nucleus is positively charged, which means there is an attraction between those two, especially electrons that are close to the nucleus, which is why when we get to bonding, there's only certain electrons that are involved in bonding. Those are the ones that are actually further away from the nucleus. They're not held as tightly. They're able to interact in bonding, while you try to interact somebody that's an electron close to the nucleus, it ain't going anywhere. It's held pretty tightly by that positive charge. So this is sort of the modern version of the atom. Nucleus, positive charge, later found protons and neutrons there, electrons in the empty space moving around, and most of the mass of the atom is the nucleus. Yeah. Most of the mass of the atom is the nucleus. Yeah. Other questions? So here is again, so what we were talking about, a nucleus contains protons and neutrons, and electrons are in that empty space, kind of travel around. This is sometimes referred to as the electron cloud, where they're traveling. And again, they are traveling really randomly about. Now, the other thing that sort of validated the idea of the nucleus being most of the mass of the atom was later experiments. And like I said, all the way up to like 1930s, when they officially sort of discovered neutrons, is where Chadwick discovered that. But if we look at the mass of these guys, which are given an atomic mass unit, which outside this chapter, probably won't use very much, which is sometimes abbreviated as an AMU. A proton is actually 1.007 AMU. A neutron is actually 1.008 AMU. And our electron is 0.0055 AMU. These guys here are actually about 1,800 times heavier than any electron that's flying around. So both a proton and a neutron is about 1,800 or so times heavier than any electron flying around. And it's actually, which one of those three particles is actually the heaviest? Is actually the neutron. It beats it out just barely. So the neutron is actually the heaviest, followed very closely by the proton. And both of those guys, like I said, is about 1,800 times heavier than any electron. So if you think about the atom where protons and neutrons are in their nucleus and our electron is flying around, it makes sense that both the nucleus is most of the mass of the atom, because inside there you have particles that are 1,800 times heavier than any electron that's flying around. So that also sort of validates the idea of Rutherford, and that most of the mass of the atom is actually the nucleus and not the electrons. Any questions on that? You do not need to know the actual masses of each of those, but you do need to know that it is the neutron is the heaviest, and our electron is actually the lightest. Yeah, and obviously our protons in between, they're very close to our neutron. Any questions on that? So you do also need to know their charges, which one is positive charge, right? Negative charge and no charge. Covered my atom there. So here's a nice table of that. Again, +1, 0, and no charge basically, and -1, and our masses. And those are symbols that sometimes are used for each of these. Usually you'll see those a lot more in sort of nuclear chemistry, but an E with a little minus is used for an electron, and a P is used for a proton, and an N for a neutron. Any questions on the atom there? All right, let's take a look at some of these. Which of the following subatomic particles meet the description found outside the nucleus is? Electron, right? Has a positive charge is proton, and has mass but no charge. Neutron. I was trying to read that. Yeah, that sounds good. In each of the true or false, the mass of an electron is greater than the mass of a proton. That is false, right? It is actually the lightest of all those. Protons have a positive charge, electrons have a negative charge. True. Nucleus of the atom contains only protons and neutrons. That is true. And here's sort of the idea of what an atom looks like. The nucleus is like super small compared to the size of the atom. So you can think of the atom as like a football stadium, and like the nucleus is like a little marble there on the 50-yard line in the middle of the stadium. The rest of it is empty space where our electrons are basically flying around. So although it doesn't take up a tremendous amount of volume, the nucleus, it does make up the majority of the mass of the atom. So, and again, the rest of it is sort of that empty space. All right. You do need to know, obviously, a little bit about those experiments that we talked about, what came out of them, and obviously early version of the atom, modern version, obviously, of the atom. Any questions on that there? So let's talk about some other aspects of an atom, which is the atomic number, the mass number, and isotopes. So as I mentioned earlier, most of the chemistry comes from really electrons and bonds being made and bonds being broken, which is all about electrons. The nice thing about it is neutrons and protons, again, in normal chemical reactions, don't participate, which means, you know, it is those electrons that participate in the chemical reaction, and we do keep really the same elements we start with as to where we end. One of the important aspects of an atom is what's known as the atomic number. The atomic number is abbreviated with a Z. The definition of the atomic number is the number of protons there are in an atom. If I have a neutral atom, and since protons are positively charged and the only other particle that has a charge in an atom is electrons, which are negatively charged, If you know the atomic number, which is the number of protons, you will also know the number of electrons because they should balance each other out. To get to no charge, which is neutral, you got to have the same number of electrons as protons. It is important to note, though, that if you were asked this question, give me the definition of the atomic number, it is just the protons, not electrons. So the definition of atomic number is the number of protons there are. Second to that is if you're dealing with something that's neutral, it will also tell you the number of electrons, but that is not part of the definition. So if somebody asks you what is the definition of atomic number, it is only the protons. All atoms will have the same number of electrons as protons if they are neutral, but if they do have a charge, they will obviously have some different numbers of electrons. The identity of an atom can be found by its atomic number, and you can find the atomic number right there on the periodic table. It is the number that comes above the symbol. So hydrogen has 1 for its atomic number, which means it has 1 proton and 1 electron in a neutral hydrogen. Lithium, which has an atomic number of 3, has 3 protons and would also have 3 electrons. Nitrogen, if you look up nitrogen there on the periodic table, has a 7 above it. It will have 7 protons and also 7 electrons in this particular case. If you look at the periodic table, which it might be hard to see up there, but if you have a periodic table near you, if you look at all the elements, do any of the numbers on top repeat? They do not, which is why the atomic number is really important, because if you know the atomic number, you know the number of protons, and you know exactly what element you're talking about. So every element has its own atomic number. You will never find a nitrogen with an atomic number of 5 because 5 should be boron when you look on the periodic table. So 5 will be boron. And you'll never find nitrogen with that because it has to have 7 protons. And that is why in a chemical reaction, as we've been talking about, we do not change the elements because they only involve electrons. We don't touch what's in the nucleus. So we don't touch the number of protons. And the only way to change the element is to change the number of protons. So because a normal chemical reaction doesn't even touch it at all, it's all about electrons, which are on the outside. That's why when we start with 4 carbons, we end with 4 carbons, because carbon will never change because the protons will never change in those guys as the chemical reaction is taking place. Any questions on that? Another important number is the mass number. The mass number is sometimes abbreviated with an A, and that is the total number of neutrons and protons there are in an atom. And the mass number and atomic number are important because the mass number is the number of protons plus the number of neutrons. The atomic number is the number of protons, which means if I subtract those two, protons cancel, that will tell me the number of neutrons. So if you take the mass number and you subtract it from the atomic number, it will tell you the number of neutrons there are in that particular atom. Everybody, as I mentioned earlier, in terms of elements, have protons, electrons, and neutrons, except, again, hydrogen. Hydrogen only, again, has a proton and an electron. It has no neutrons. Everybody else has neutrons. When you are asked to calculate any of these things, the number of protons, electrons, and neutrons, the mass number or the atomic number, they all have to be positive whole numbers. That's a really important thing to remember, yes? Because my next question is, can I find the mass number on the periodic table? So for example, if I look at hydrogen and it says 1 and 1.008, or I look at carbon and it says 6 and 12.01, is the mass number up there? The answer is no. Those are not the mass numbers, right? Because as we just saw here at the very bottom, what does it say? Mass number, atomic number, protons, electrons, neutrons need to be what type of number? Whole number. Are those whole numbers? If you look on the bottom of the periodic table on all those elements, there's pretty much no whole numbers. They're all decimals. That's the way to remember that. And this is actually what is referred to as the atomic mass, which is different. So the mass number, not on periodic table, yes? And what confuses people a lot of times is the mass number and the number that you see on the periodic table. In a lot of cases are very close to each other. They're very close to your number. So people think, oh, they just must have rounded, and that's how they got the mass number. So that's, again, not how you get it. That is the atomic mass. You will always have enough information in these type of problems to figure out the number of neutrons, protons, electrons, mass number, and atomic number. The only actual number that you could get from the periodic table is only the atomic number, which is the number of protons. So don't be the person that will write that number on that test question. Yes, there's always a lot of people sometimes do that. So any questions on that there? So let's talk a little bit about isotopes. Isotopes, as I mentioned earlier, are the same element, but they do not have the same mass. And that basically means that they have different numbers of neutrons, which means that's why they have different masses. A very common way that we write sort of isotopes is with the mass number on the top left and the atomic number on the bottom left. So for example, we have hydrogen, which has 1 proton and no neutrons. We have deuterium, which has 1 proton and 1 neutron. That's sometimes referred to as heavy hydrogen. And we have tritium, which is like the radioactive version of hydrogen, has 1 proton and 3 neutrons. So if we were going to write the symbols for each of these, this is how we would do it. The most important thing to know which element we're dealing with is the number of protons, right? So I see 1 proton for hydrogen. If I'm not sure what that is, I go to the periodic table. I find number 1, and it shows me that the symbol there is hydrogen, which is H. So that is what I would write. Atomic number goes bottom left, which is 1 in this case. Mass number is protons plus neutrons, right? So the mass number here would be 1 plus 0, which is 1, which means the symbol for hydrogen would be 1 on top and 1 on the bottom. Top number, again, is our mass number. Bottom numbers are atomic number. And basically, if you have it written like this, I take the top number minus the bottom number, gives me 0. That is the number of neutrons, right? So top number minus bottom number will give you the number of neutrons. Now, let's say we got to deuterium. Doesn't sound like hydrogen, right? Funky name. But what I know is it has still 1 proton, which means when I go to my periodic table, that's still going to get me the hydrogen. So the symbol for that guy is still hydrogen, because it really is still hydrogen. And it still has an atomic number of 1, which is the number of protons. But when we get to this guy, it has 1 proton plus 1 neutron, which means it has a mass number of 2 in this case. And that 2 should go up on top. So if I take 2 minus 1, I get 1 neutron that's left over in that case. That would be the symbol for deuterium, which really is which element still? Still hydrogen, even though it has a different name, right? So if we look down to tritium, which also doesn't sound anything like hydrogen, but when I see it, it has 1 proton. So again, I go to the periodic table, I see number 1 is still hydrogen, so the symbol there should be H. Once again, the atomic number should go bottom left, and the top number now is 1 proton plus 2 neutrons, gives me 3 for my mass number, which means my mass number should go like that. So those are all 3 symbols, 1 for hydrogen, 1 for deuterium, 1 for tritium. Even though they all 3 have different names, they're all 3 the same element. They all 3 also have different masses, because one has no neutrons, right? One has 1 neutron and one has 2 neutrons. But because they are the same element, they will have some different masses. This is why Dalton's atomic theory that we talked about earlier, incorrect in this aspect, because these are all the same element, but each of these atoms have different numbers of neutrons, which is why they're not identical to each other. Any questions on that? Yeah. No, no. So this is just an example that maybe in a problem, you may be given a name that's like, I have no idea what element that is, but maybe they give you the number of protons. So again, you could just simply go to the periodic table and figure out really what element it is. And sometimes there are different names for different elements depending on, the isotope that you're dealing with. Another very common way that isotopes are written is something like this, Cu-64. That is sometimes referred to as copper 64. Remember that? That's radioactive, by the way. That's like a 3-day radioactivity before it dies. So in this case, copper 64, the 64 would be what number, you think? Well, I know for sure if I go to the periodic table and I find copper, what number does it say above it? I think it says 29 above it, yes. So that is the atomic number, right? So I know that that 64 is definitely not the atomic number. So that is most likely the mass number, right? So if I were to write this the other way, 64, which is the mass number, should go up on top, and 29 that I could get from the periodic table should go on the bottom. That would mean that this copper right here, the number of protons, how many does it have? Number of protons is the atomic number. So what's the atomic number? 29, yeah. And it has no charge because there's nothing written there, which means it's neutral. How many electrons should it have? It does need to have 29, yeah? So 29 positive things, protons, right? And 29 negative electrons, when you add those together, no charge. Yes, that's why it does not have a charge. The number of neutrons in this case should be our mass number minus our atomic number. And that feels like a lot of math at this late hour, but I can go with 35 and hope for the best there without picking up the calculator. Give or take a neutron along the way there. Hopefully that's right. So that's 35, which would be the number of neutrons. So here you can see I got all that information, right? Protons, electrons, neutrons, mass number, atomic number. I did not go to the periodic table to take any decimals. You will have enough information to calculate all those things based on what you need. Any questions on that there? All right. All right, I think we'll lay it up there, I think.